Chapter 18, my career. Now buckle up, this is going to be a long one. First of all, it starts out with a really good picture of Dad there. The caption says, Fluid Power Engineering, my career. It seems as though my career developed through a series of sequential events beginning with my time as a teacher at the Missoula Technical College. It was there that I realized how much I loved teaching and even more technical subject matter. Shortly after being hired by the Votech, I was asked to develop a hydraulic curriculum. I had very little experience in this field, but immediately took to it and loved it. Little did I know that chain of events would lead to a wonderfully satisfying career. After the end of my second year, Darling and I decided that it was best for the children to if we moved to a new location. Darling, of course, being Mom. This would allow them to grow up without the stigma of their past, which I noticed especially at church. I received an offer from one George Lawner to teach basic hydraulics to some companies that he was providing technical training to. It was a very hard decision to leave the Votech, but I had a strong feeling that I should. Career-wise, it was the best decision I had ever made. I was going on blind faith, but I accepted George's offer. As it turned out, my first training engagement was in Utah at the Southwest Cement Company in Delta. From there, I went on to the apprentice training at the International Power Plant in Delta. It had just completed construction and was hiring people with little to no understanding of fluid power. The term fluid power applies to both hydraulics and pneumatics. As my understanding of this technology grew, I wanted to move to the design and troubleshooting of hydraulic systems. I passed through 3 companies over the next decade, learning more and more. I passed a very difficult hydraulics specialist test and became a certified instructor and specialist. This was a requirement to do work for Thiokol. During this time, my name was submitted for consideration to be a board member for the International Fluid Power Association. There were a fair number of people from my peers in the industry that were also recommended. A poll was taken by members and I was selected. I served on the board for 3 years. I met many people in my industry while on the board. It was there that I met another member from the Boeing company that eventually led to consulting and training for Boeing Seattle. During this period, I had done a lot of troubleshooting of hydraulic-related failures at Geneva Steel. My understanding of fluid power had nearly peaked by then. Kennecott hired me to design a central hydraulic system to replace their current systems that were outdated. It proved to be a great system that is still operating today. As the internet came about, I recognized the incredible opportunity to provide basic training in hydraulics, pneumatics, mechanical, and control in digital form over the internet. A year or so later, I had an idea that vastly reduces the amount of time to troubleshoot machine tool systems, using digital assets from the machine by putting content into context. Boeing immediately recognized the value. It was applied to all the Boeing machine tools in Renton, Seattle. I then applied for a patent. I was told that my idea could not be patented. I went to see Curtin and McConkie, one of the best legal firms in Salt Lake. And after studying my idea, they were confident that it was patentable as a process patent. About 2.5 years later and $45,000 later, I received the patent. About this time, I was doing a lot of work by applying my application into the steel mills. I became a member of the Association of Iron and Steel Technology. The following year, I was chosen to be the chair of the Hydraulics and Lubrication Committee in Maintenance Reliability. A few years back, I presented a white paper to the Association of Iron and Steel Technology at the yearly convention. It was published in their magazine. As time went on, Wes, another son, saw greater opportunity in adding improvement to the patent and the cloud base. He put a lot of time and money into building the back end and other improvements. He is the perfect partner. The company continues to thrive under Wes's leadership and direction. At one time, I thought I would half retire. It has become the opposite. I absolutely love what I do and have dozens of friends in the industry. I'm now looking at age 75 as a great time to step away. Maybe. Let's give a good shout out to Wes, shown here on the job. I've included in this story a copy of the published white paper. I have included it because my application is somewhat difficult to completely understand if you're outside of our industry. After a careful review, you will totally understand, I hope. My white paper is as follows. Deep breath. A new generation and a new process. An application that can do for technicians what CAD does for engineers, or for engineering, by Brad E. Jensen. Introduction. Today, industry is faced with a serious shortage of skilled technicians while the drives and controls of steelmaking equipment become ever more sophisticated. Compounding the problem is the increasing demand for more uptime to offset non-recoverable downtime. This paper presents a process that combines the new generation of technicians with a technology tool that can put them on par with those having much more experience, hence growing a more efficient upcoming generation of troubleshooters. More efficient because of the incredible technology tools that are now available, formatted and applied into the industry at an ever-growing pace. A recently patented application titled iSchematic, engineered particularly for the Y generation, or Gen Y, of technicians, may very well do for them what CAD has done for engineering. Many of the boomers remember and have followed the birth and evolution of AutoCAD in industry. Developed and marketed by Autodesk, Inc., AutoCAD was first released in December of 1982, and by 1986 was the most ubiquitous microcomputer design program worldwide. More important, CAD technology has changed how engineering system design is practiced and has clearly been a major element in the increase in industrial productivity over the past 2 decades. Although far from being able to predict the exact technology that will change the process of troubleshooting sophisticated industrial machines, assuredly, change in the current approach of the process is beginning to evolve. The following is an example. The process of taking existing machine documentation and converting or filtering it to become contextually specific for maintenance application and deliverable over mobile devices will forever change for better the way troubleshooting equipment is done. The boomer generation of maintenance technicians is passing the baton to Gen Y. As this transition takes place, tribal knowledge, skills, and procedures can be captured and digitally passed on to a new generation, inherently prepared to combine that captured knowledge with technology tools. A new generation. The Y generation, sometimes referred to as millennials, is the tag given to those born between 1977 and 1995, more broadly expressed as those born between the late 70s and early 2000. Gen Y consists of approximately 79.8 million people in the United States. They are currently the fastest growing demographic in the workplace and the marketplace. They are an emerging adult population that exerts more influence due to their sheer numbers, expected longevity, and hyperconnectivity. By 2020, nearly 50% of the U.S. workforce will be Gen Y. As this new generation replaces the boomers in industrial maintenance positions, they bring with them some interesting characteristics and background in terms of who they are. In short, Gen Yers want stimulating work that gives them a large amount of opportunity for learning and growth. They are not necessarily tech savvy, although they are absolutely tech dependent. They were born with computers and software programs, none the least being gaming programs. They are tremendously versatile with web delivery and mobile technology. They're extremely visual and rather impatient for data. Generally speaking, they prefer to communicate digitally. They seem to have an inherent ability to understand a software program's algorithms, being able to navigate around within minutes. As boomers and Yers come together in the workplace, the integration and handoff of learned skills, procedures, and general knowledge can have its challenges. However, this convergence is also a time of tremendous opportunity for work together and leveraging what is currently had as optimum skills and knowledge from a retiring generation to a new generation. This union will greatly increase maintenance reliability by using knowledge of the past with present and future technology. A new process. In reflecting on how learning a machine's operation, maintenance, and troubleshooting is approached, most likely the technician begins with the documentation that accompanied the equipment at the time of installation and commission. This is usually found in a paper manual, on a CD-ROM, what's that? Or on the web and supplied from the original equipment manufacturer, or OEM. Although the content is readily available in abundance, it is often difficult to search and can have contextual issues as it relates to maintenance. In the current world of technology, this type of documentation is cumbersome and difficult to use, making nearly impossible the quick location of information relevant to a specific issue with the machine. Additionally, changes made to the drawings and schematics during commissioning often have not been updated. The case here is that frequently how documentation is presented in an asset that is challenging at best when used in troubleshooting during unscheduled machine downtime. Consider another aspect of the maintenance process, training. While training is a critical element of the technician's growth and skills development, it is very often misapplied. If no strategic outcomes are developed around the training, it can be a very expensive element in the process with little or no return. Training must be considered an event, while learning ought to be looked at as a process. In today's industrial maintenance processes, training is offered in many formats, with various methods of delivery. For training to have a positive return on investment, it must have defined outcomes that always connect to reducing unscheduled downtime from equipment failures, or it should always be considered an element of learning or construct. In the skills learning and development triangle in Figure 1, which I'll show in a second, notice that training is offered in several formats, selected purposely for efficiency with specific outcomes. For example, e-learning is a format that facilitates moving a technician from awareness to comprehension. This can be accomplished efficiently with on-demand delivery on the company's time, and often in the company's place. Although the same outcome could be achieved placing a dedicated instructor in a classroom with a group of off-the-floor technicians is an inefficient and expensive choice for delivery. Technology now allows the accomplishment of good results with very little cost, and if developed correctly, the acquiring of even better results than classroom delivery, provided the subject matter is foundational, wherein movement is from awareness to comprehension. Notice that when skill advancement passes the comprehension level and moves into the technical level, classroom instructor-led training provides the most effective outcome in terms of content delivery. And here is that triangle he was referring to, right there. Described as the skills, learning, and development triangle. In the skills, learning, and development triangle, time on the job is essential to progressing up the levels. This has sometimes been erroneously used to determine skill levels, while no metrics are used to measure outcomes. The triangle suggests that various formats and deliveries of training over time on the job facilitate learning and skill development. Mastery is shown as the highest level of development and is measured by a technician's ability to efficiently and safely troubleshoot a machine's failure. Understanding the unique qualities and characteristics of the Gen Y technician is essential in selecting skill development strategies, including tactical approaches. Careful consideration should be given to selecting how content is delivered, when it is delivered, and to whom. Remember, Gen Y learns differently than the boomer technicians, yet this older generation holds vast amounts of knowledge and skill and can be a powerful asset in assisting with this knowledge transfer to the incoming generation. Though time on the job will always be a required element to some degree, the mastery level of skill development can be reached in a much shorter period of time while developing a safer process for troubleshooting. This is achieved by organizing the machine's documentation content into the right context, while using technology to place it no more than 3 clicks away. The content must also be updatable and web deliverable for complete access and collaboration. This process is called iSchematic, patented in April of 2013 as Methods and Systems for Machine-Related Information Delivery. U.S. patent number 8,401,675. B2. The process of applying the iSchematic tool as a construct of skill development and machine-specific troubleshooting moves most technicians immediately from the comprehension level to the skilled level. It also enables the more skilled technician to have mastery when applied to a particular machine. Organizing and documentation. The iSchematic process of organizing and documentation begins with collection of the all machine data, including engineering drawings, schematics, operating and maintenance manuals, controls data from the PLC, and other documents that are relevant to the operation, maintenance, and troubleshooting of the machine or equivalent. I meant to say troubleshooting of the machine or equipment. A subject matter expert reviews the documentation and then separates and categorizes it into the following metadata files: machine operating events, hydraulic, pneumatic, and electrical schematics, process flow diagrams, bill of material documents, I/O listings, controls ladder logic, component images, image files, and video files. The file assets are verified for accuracy and any required revisions. Drawings and schematics are redrawn with color-coded legends and saved as CAD files for quick updating, as illustrated in Figure 2, which is this little figure that you can't really see very well. That's Figure 2. The schematics contain the original documentation and include any revision changes. Critical component symbols are identifiable and will be hyperlinked in the tool to an image of their respective device. Images are taken of all relevant components with their specific part numbers, manufacturer's data, stock codes, and PLC addressing, then loaded to the database. Additional files that are added to the tool are applicable MP4 component learning modules. Every component on the machine that is identified as an asset of the project is assigned an animation that will or has been developed to illustrate the functional description of the device. It is generic and not manufacturer specific. For example, if a machine is utilizing an inductive proximity switch as an input device in its controls, then an animation of this type of proximity switch is hyperlinked to the component data page of the iSchematic tool. The machine's control data, or PLC, is organized and separated into files containing the I/Os with their respective component data and electrical schematics. The PLC ladder logic files are reviewed to help formulate the machine's events listing and also reference the specific I/Os that are associated with each event. The controls documentation is put into context that assists the technician in associating inputs with outputs by viewing the PLC ladder logic. Once all the machine's documentation assets are entered into the database, they are pulled together into the application editor, creating a tool that is referenced as iSchematic. The iSchematic tool provides the technician with a user interface, displaying the machine's events as well as the other drill-down titles, with content mapped and hyperlinked. Figure 6 shows an example of the user interface page for the B1 shear at Nucor Hertford. For illustration purposes, this particular machine is used to show features on the iSchematic application, and here is that Figure 6, the user interface. A machine's functional operations and or failures often are communicated first by referencing the machine's specific event or events that are malfunctioning, thus establishing a firm base from which to begin the troubleshooting process. Any number of events, which are determined by the type of drives that are performing the machine's work cycles, can be used and are listed on the user interface. Most often these events are established from the PLC register or registry or ladder logic relative to the machine's inputs and outputs. The B1 shear's event type of this machine is hydraulic. Although not shown in this user interface, the PLC controls are also included for most of the hydraulic events, which is critical for the technician to distinguish and separate hydraulic failures from electrical failures. For purposes of example, the shear cylinder down event is emphasized on the user interface, indicating an event that is not functioning correctly. When the technician clicks this event, it is immediately hyperlinked to the hydraulic schematic, showing the circuit with the applicable coloring that indicates flow direction, flow control, pressure variations, and mapping through the symbols that represent the specific hydraulic components associated with this particular event. This screen also has a drop-down text box that describes in detailed text form what is illustrated by the circuit board or the circuit color legend. In other words, the screen will have a step-by-step explanation of the sequence of operation and its related components. As the technician evaluates the data associated with the event, he is learning to read the schematic and learn the symbolic or the symbol logic, an invaluable skill to develop for use in troubleshooting hydraulic failures. He also has immediate and accurate data on what circuits are under pressure, also an invaluable safety tool. Although lockout, tagout procedures prevent a multitude of hydraulic-related injuries from occurring each year, they generally never give protection against trapped pressure exhaust hazards. Another challenge is faced at this point in the process. Normally, when reading or analyzing a schematic, a technician may be successful in determining what components may be contributing to the outage. Yet, even some experienced specialists find difficult, if not impossible, knowing where a particular symbolic identified device actually is on the hydraulic valve stand or elsewhere in the circuit, a real problem in troubleshooting and in safety. By hyperlinking the circuit symbol to the image of the actual device, a costly error can be avoided. Figure 8 illustrates an example of clicking on bubble number 9.2, a crossover relief valve in the shear cylinder down circuit. And figure 9 illustrates the component screen that is hyperlinked to it. So there's the first schematic, and there's the picture that shows up when you click on the right number. At the component data screen, a wealth of information is just one click away. The information that can be attached to the component at this point is limited only by how much data the technician wants to connect. The default data includes the following: component drawing number, component description, manufacturer, and the manufacturer's part number, the CMMS stock code, the store location, the component application, in other words, what is the device doing in this circuit, the actual device image showing the description or showing the location, the animation showing the functional description, video image of adjustment or removal, safety related data or procedures, manufacturer's data sheet. An important feature to note here is that the learning module or animation that is part of each device's data page is the same module that the technician learned from if he or she participated in the basic hydraulics, basic pneumatics, basic electrical, basic mechanical, or basic drives and control e-learning used to progress from awareness to comprehension. With each new machine application that has a missing animation describing the functionality of a device, a learning module is created. The module now can be used in the machine's iSchematic and can be accessed in e-learning or in a wiki search format. The animation attached to a crossover relief logic valve has a default animation on pressure control logic, on the pressure control logic valves. Once the machine assets are in the database, they can be pulled up from a number of locations. One such place is from section 5 of the user interface. With all the machine's components tagged and a search engine in the tool, simply do a search by part number, manufacturer, or description. For example, in figure 11, the word logic is entered in the search box, and immediately the component is filtered from 421 components identified and linked to the component data screen. There's a little search option there. Beyond the actual iSchematic troubleshooting tool itself is a vast library of growing assets contained in the system's metadata. The technician can access this through an internet connection. It is a resource library of growing assets that are shared by all utilizing this technology. It was built on the concept of wiki technology and allows the technician to simply type in a keyword for a device he wants to learn more about. Once the topic is selected, the system opens a search that allows him to view animations on the device's functionality, view a movie on a procedure, or view text that gives descriptions or definitions, in addition to images that show component applications. In Figure 12 is a screen capture illustrating an example of a video showing a change or configuring of the X and Y porting of a pilot operational control valve. Little change of scenery. Another important consideration when integrating this type of digital tool is the ability to make edits. Machine specs, components, and critical drawings can change over time. The editing capability needs to be somewhat intuitive and with few steps in the process. Editing tools have advanced quickly with technology, allowing text changes to be less than 4 clicks away. Replacement or adding of images and videos is a few steps more, but certainly very easy to accomplish in a short period of time. Uploading CAD drawing changes can be a bit time consuming, but thanks to more illustrative user manuals and instructional video, this too can be learned in a reasonable amount of time. Figure 13 is an example of a text field editor showing the component data referenced earlier on a pressure valve in the shear cylinder down event. Notice that it only requires opening to the text field, making the needed changes, and then saving it. Little graphic there. As utilization of mobile device technology grows, the devices themselves become increasingly more compatible with metadata storage and suggests a powerful way of troubleshooting industrial equipment. The iSchematic tool is already iOS compatible for use with the iPad with a downloadable app at the Apple Store and is fully compatible with the Windows 8 software running on mobile devices. Security may be an issue in some cases, however. The tool can be placed on the inside of a company's firewall. Figure 14 is the iSchematics tool system data, which is there. Results. At Nucor Hertford, iSchematic technology has been applied as a key element for assisting in the successful reduction of unscheduled downtime. The technology has been integrated into several areas with specific application to machines that are critical to reliability. Currently, it is being utilized as a troubleshooting tool for hydraulic circuits in the EAF and rolling mill, with scheduled integration as part of an ongoing process. Over the next 5 years, the iSchematic technology has been applied to approximately 60 segments of steel production equipment throughout the industry. I should say over the past 5 years. Nucor Hartford assisted in creating metrics that show results relative to ROI within their application. Although this is an ongoing study, Figure 15 gives current results of one aspect of the ROI as applied to non-scheduled machine downtime in mill bending. And there's the chart that shows that. The first half of year 2013 shows an uptick in downtime due to one situation. During a scheduled downturn, a problem occurred that had to be calculated in part as non-scheduled. This is left in to ensure an accurate metric. The trend, however, as shown in the graph in Figure 16, shows a continuous improvement of over 50% in unscheduled downtime in year 2013 from the year 2012. A closer study in 2014 will trend another aspect of the total ROI, tracking skills improvement with respect to technicians assigned to equipment that has integrated iSchematic technology, which shows a nice downward trend there. Currently, different technicians are assisted or assigned to assist in each new integration, giving them unique training, not only on the equipment itself, but in the understanding and application of the technology. During the process of upgrading to the iSchematic, the hydraulic technician becomes fully engaged in understanding how the company's hydraulic systems work and is 100% included in any modifications that need to be made in the machine's documentation, including errors in the schematics. The constant interaction between the hydraulic technician and the iSchematic project engineer builds new understanding on the machine's operation and functionality, and additionally builds understanding of how the technology maps quickly to identify failure sources by component. In summary, the technician's involvement in this course is a course in ice schematic application for that specific machine. This process helps prepare the technician for future situations that will occur, and also gives them the applied knowledge to help train others. Other industries' application results trend in a very similar way as Nucor Hartford's. To date, ice schematic technology is being applied extensively in the following industries: steel, pulp and paper, oil and gas, mining and aerospace machine tooling. Companies such as Boeing, Halliburton, and Barrick Goldstrike have measured outcomes that have produced similar results over the past 5 years. Industry trends that are associated with this technology, such as mobile devices, web delivery, video capturing, and other growing applications, will assist in improving these metrics. Additionally, this same technology will be justified in areas beyond power transmission and motion control technology. Areas such as steel industry, vacuum tank degassers, system water management, plant air, and aspects of lockout, tagout. The results can be significant in maintenance and reliability, with its subparts of documentation, troubleshooting, and skills development and safety. Conclusion. During the transition period from some of the industry's most skilled technicians to a new incoming generation of maintenance workers who bring with them unique and valuable abilities, it is critical that the baton is not dropped when transferring what may well be the largest combined amount of critical knowledge the industry has ever known. With a timely convergence of new technology occurring at the same moment in time, it is possible to accomplish not only a safe conferral, but actually leverage company-specific knowledge, documented and undocumented, and acquired skill to a new level of maintenance and reliability efficiency. The ice schematic tool reviewed in part in this work is but one of many applications available to assist in this process. If accomplished, great outcomes will be seen almost immediately in terms of a reduction in non-scheduled downtime with company equipment, while simultaneously the knowledge and expertise of these incoming technicians move up rapidly in the skills and learning development triangle. Embrace the new technology and the new generation of technicians. They go hand in hand. There's a large list of references that goes with it, and it says that this is the patent that I applied for and was awarded. That is the pinnacle of my career. It is also the core of what my business actually provides the industry that I work in. And here is a copy of that patent award. That's it.